Hello, in this video we're going to look at multiple linear regression in canonical form and assume that there's multicollinearity in the design matrix. Now this is sort of a follow-up video to a video I have just called canonical form, or multiple linear regression canonical form. So here we assume the model is y is equal to beta 1 x beta plus error. And a lot of times this piece is encompassed in here where the first column is all ones, but we're separating it, and we're going to take this matrix and center and scale it and assume it's full column rank. Now the least squares estimate for beta when the design matrix is centered is y bar. So if we subtract that over and just plug in y bar, so we take our y data, subtract the mean from each element, and call it y star. And here we put in the identity matrix, a well-chosen identity matrix, V prime, where that is the identity matrix, and V is a P by P matrix. Actually, it ends up being orthonormal eigenvectors, which we'll talk about in a second down here. And actually, there's more in this video, just called canonical form. So here, the V prime B we'll call gamma. And here there's P columns, so we'll take X times each of those, creating P columns, right? Each of these is a column, and N by one column, and this is a P by one vector. It's actually very similar to this right here. There's P columns, P by one vector, P by one vector. Very similar. So here, let's assume that X is ill-defined, and let's let the eigenvalues 1 through r be greater than epsilon, and eigenvalues r plus 1 to p be less than epsilon. And this is where the eigenvalues, or the lambda i's, are eigenvalues for x transpose x, and v are the associated orthonormal eigenvectors. And I would say see previous video 40 and previous video 56 in this playlist for more detail on this. Now, one of the nice things about the canonical form when there's multicollinearity in the design matrix is we can separate these columns. Well, it turns out the columns associated with larger eigenvalues, they span a set that's not ill-conditioned, and then the columns that are associated with eigenvalues less than 0, those are all associated with very, very small vectors, or ill-conditioned vectors. And so if we get rid of those and keep the rest, we're really not losing much information. And actually that's the basis of principal components, which we'll talk more about next video. But here we want to just show that we can do that we can split this matrix into the information and then ill-conditioned information, matrix, vectors that are really small. So let's show that the first R vectors form an orthonormal basis, an orthogonal basis for a subset of the column space of X, which all vectors are not ill-defined. Okay, so first the vectors are independent, and mathematically we say they're orthogonal. So we take, we're going to assume the inner product, the standard inner product for our inner product, and that's vector product. So if we look at this, we take the ith column and the jth column, and distribute the transpose, we get this. But V is an eigenvector for x transpose x, so we can replace it by the eigenvalue and eigenvector, which is what this is. And then if I and j are not the same, since they're orthonormal, that's 0. And this is, if I and j not equal from 1 to r. So they are independent, and thus form a basis in R space. And now since R is actually less than the rank of X, which is P, this is a subspace for the column space of X. Now let's let X star be these first R columns, and let this be a vector in the column space of X star. And this is for some B in R space, right? Because since there's R columns here, B, when you multiply it, has to have R columns. And we'll just generically let B be B1, B2, to BR. Now this is the condition that we set up for condition matrices. And I have a video called condition number, multiple linear regression condition number, for background on this. So this is the criterion. So now let's distribute that transpose. But if you think about it, actually let's wait on the transpose. This product here, when you multiply it, it's the first component times the first column, second component times the first column, all added together. And that's what this is, right? So this is the first, when I is 1, that's the first column, first component, added to the second column, second component, right? That's the same way here. Now let's take the transpose in, and since it's a sum, you do it term by term. This is a constant, so it can stay out front. So those are reversed. And then we combine the sum, and we get this. Now this is an eigenvector for x transpose x, so we can replace it by the eigenvalue and the eigenvector. Now this product is 0 when I and j are not equal. So when they're equal, it's 1. So this makes it a single sum, and I and j are equal, so that's bi squared. Now we're assuming the lambda i's are all greater than or equal to epsilon. So if we put in epsilon here for each lambda, this gets smaller, but we can take it out of the sum like this. Those cancel, leaving epsilon, and epsilon is definitely greater than or equal to epsilon, which says this condition is greater than equal to epsilon. So they're not ill-conditioned vectors. It's not an ill-conditioned matrix. So note that the column space of x star is a subset of the column space of x, and all vectors in the column space of x star are not ill-defined, and thus the result follows. Now let's show that the remaining columns are plus 1 to p, so there are p minus r columns here. We're going to show that they form an orthogonal basis for a subset of the column space of x, in which all vectors are ill-defined. It means they end up being really small. They don't carry much information. The vectors are independent, meaning orthogonal, and so similar to I, it's easy to show that this vector product is 0. Same approach, and this is when I is not equal to j, and I and j from r plus 1 to p, right? So each column is orthogonal to the next, which means it forms a basis in p minus r space. So now let's let x double star be these n minus r or p minus r columns. Now since the rank of x double star is p minus r, which is less than p, which is the rank of x, that shows that the column space spanned by x double star is a subset of the column space of x. Now let's let this be a vector in the column space of x double star. Now here b is not the same b we used in I, but when you do that multiplication, it has to be p minus r, diminished by 1. And this is for some b in p minus r space. So now let's look at this condition and to see if these vectors in the column space are ill-defined or not. And so we set up this condition. And now very similar to number 1, boom, 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 we get to this sum. Now all these lambda i's are less than epsilon. So if we put in epsilon for each one of these lambda i's, we're making this bigger, but it's not indexed, so it can come out front, right, of that sum. And of course b prime b is the sum of bi squared. So those cancel and we're just left with epsilon. So all of these vectors are less than epsilon. So every vector, let's just say it, so which implies that all vectors in the column space of x double star are epsilon ill-defined. So they end up being very small. And so that's actually one cool property about the canonical form when we have multiple linear regression, is we can separate that matrix into all vectors that are not ill-defined and the ones that are ill-defined. And we can get rid of the ones that are ill-defined and then just use the other ones. And anyway, that's the next video. So now in 3, we want to show that the column space of X is actually the span of both of these columns. So let's go this way. So let's let this be a vector in the column space of X. So X is in by P. So this is a P by 1 vector. This is, okay, for some B in P, or, in P space, then B can be written as VC. Now V, remember, those are orthonormal eigenvectors. This is a P by P vector, and they're all orthonormal. So they span our P space. So we can write B as a linear combination of those vectors for some C in P space. So now let's let X be, and we're going to write out what B is. Remember, this is V, so there's P columns, and that's C. Now if we split this, so if we take the first R columns, and then the last P minus R columns, and then split C into C1 and C2, so this multiplication works, right? We get this. But this is in the column space of X star, and this is in the column space of X double star. So a vector in the column space of X is actually in the column space of these two subspaces added together. Now let's go the other way. So let's let B be in this subspace, or column space of X plus column space of X double star. Then B can be written like this. So it's a linear combination of the columns of X star plus a linear combination of the columns of X double star. But this is the same. So like if we back this out, so we take the X's and factor them out and then take it out. And then we can write the V1 through VR and the VR plus 1 to VP like this, right? Where C is, C1 and C2. But then this says that it's in the column space of X, right? So there's X, and this is a vector. So a vector in this column space is in this column space. And that's what we wanted to show. All right, well, that's all I have for this video. The next video, we're going to talk about principal components. We're going to make use of these ideas in this video. So I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.